Consider, can we see? Consider, okay, just the background, especially because of branding. What we are trying to do today is the idea of dependent and independent events. As I'm going to write very soon, from the word dependent, they depend on each other. Independent means they do not depend on each other. So, in mathematics, we say that events A and B are independent if whatever happens to A does not affect what happens in B. So we say if the occurrence of A does not affect the occurrence of B. And of course, the non-occurrence of A does not affect the occurrence or the non-occurrence of B, like we're independent. Okay? In the same, the other way around, if it is dependent, of course, what happens to the first one affects what happened or what does not happen to the second one. So that's just the summary of dependent and independent event. And these two tasks are meant for you to be able to investigate what is the relationship between the individual probabilities, if there is any. So, for number 2, it says consider a randomly selected ball from each of the boxes. So you could see from here, there are 2 blue, if V is blue or black, we don't know. Oh, blue, because of the color. And 2 green. Here we have 3 red and 1 white. So the first is to say that, does the outcome of the draw from each box affect the occurrence of the other? Does it? Whatever I pick here, does it in any way affect what I pick here? So for example, if I pick a blue, does that stop me from picking a red or white in the other one? Okay, so since it does not, then the drawing a particular color from here and drawing a particular color from here are independent events. That's the whole idea. Now, the first thing is to draw a 2-dimensional grid of all the possible set of outcomes. So if this is box 1, then this would be our blue, and this would be our green. So this would be our red again, then white. So which means the sample space consists of their point of intersection. So can someone tell me what is the cardinality of the sample space? 16. So the cardinality of the sample space is 16. So whatever you do is divided by 16 basically. Now, to complete this table, A is the event that you select green from box X. If you select green from box X, so maybe I should write here X and Y. Box. Selecting green from box X means these possibilities. We don't care what happens to the vertical axis, right? The vertical lines. We are interested in this. There are 8 out of 16. This will also be 1/2. Blue from X, oh, same. 8 out of 16, which will be 1/2, so similarly 1/2. Selecting red from Y, okay, red from Y. Again, we are not particular about this. Red from Y, 3 places in 4 lines, that's 12, right? 12 out of 16, which is 3/4. So similarly, 3/4, yes? And white from Y will be 4 out of 16, 1/4, of course 1/4 again. The last column is not for you to multiply. The multiply is what you are supposed to obtain eventually as your deduction from this investigation. Okay? So the last one, we've mentioned what intersection means under combined event. Abi, right? When you say combined event, A intersection B is used to represent the event that A and B occur. So A and B occur in this case means there's a green from X and a red from Y at the same time. So you go to your green from X, you go to your red from Y, and you look at their point of intersection, and they intersect in 6 places out of 16. So this is 6 out of 16, which is 3 out of 8. The idea is that when you multiply it, you realize it's equal to this, but you're not supposed to multiply it immediately. Okay? Again, green from X, but white from Y, green from X, white from Y, 2 out of 16, which is 1 out of 8. blue from X, red from Y, similarly 6, right? Right? And the last one also, is it? Blue from X and white from Y, 2. So this is 6 and this is 2. So you have 6 out of 16, 2 out of 16, 1 over 8, 3 over 8. So to deduce, what the third question asks you to do is to now examine the table in figure 1, in the question 1, table in question 2, and see what you notice. And what we have noticed is that the probability of A times the probability of B will be the probability of A intersection B if the events are independent. So the first thing that comes to you is, are these events independent? You have to be able to use your intuition to be able to deduce that, oh, actually, what happens to A does not in any way affect whatever happened or whatever does not happen to B. Because probability question will be a real life scenario. Yeah, it's going to be in a hypothetical situation. Oh, suppose Karen sleeps yesterday. Oh, suppose Karen hits yesterday. Oh, suppose Mr. Chang is sleeping right now, which is trying to sleep right now. Okay, now. Okay. All right, so the third part of the question will be, for independent event, what is the connection? The connection is that probability of A intersection B is equal to probability of A times probability of B. Okay? Okay, so instead of me writing it that way, let's not write number 3. You've already done that, I'm sure. Let's write the definition of independent event here. So let's write quickly. So summary of our investigation. Or definition. Both. 2 events, A and B, actually 2 or more, it could be extended, so let's say A and B first, are independent events if the occurrence of A does not affect the occurrence of B. And of course, even the non-occurrence as well. In this case, probability that A and B holds is probability of A times the probability of B. So that is the summary you can get from here. And I've also asked you to do this. Let's look up. Suppose a bag contains 3 red pens and 2 blue pens. Mr. Daniel wishes to pick 2 pens from the bag. Whatever reason, we don't know. But that's his problem, right? Not our problem. That's his problem. Do you know who that is? No. Okay, me too. Does the chance, what did I say, change? Oh no. Does the chance of picking a color from the second, picking a color for second pen depend on the first pen? Does it? Yes. Karen? Correction? Yes, of course. It does. Okay, that's one part. So this is to establish that in this case we have dependent events. Okay, so let's see the possible scenario. If you are to pick 2 pens, one after the other without replacement, of course we know that we have a total cardinality of sample space is 5, isn't it? Right? It's 5. Everything is 5. So we want to pick 2 pens. 1. If I want to pick 2 red, the first is red and the second is red. Because I do not replace, what is my chance of picking the first red quickly? 3 over over 5, and the second being red, 2 over 4. Because I do not replace. And that gives me 3 over 10. You cut, you don't. This is not baby class, right? You don't need to say 6 over 20 is equal to 9. Come on. I may decide to pick 2 blue. And that will be 2 over 5 times 1 over 4. 1 over 10. 3. I could pick 1 red and 1 blue in any order. I'm going to get the same thing. So it could be red first before blue, or blue first before red. This is another scenario. So if I pick red first, 3 over 5, then blue, 2 over 4, isn't it? Then I get what? 3 over 10. It's just a coincidence. Okay? It's just a coincidence. Then here, if I pick this first, 2 over 5, 3 over 4, also we have a coincidence. So you can see we're going to get different chances. Okay? So as a result, our chance, these two events are like that, so which means this is our summary here. Let's have the summary or definition again like we did the last time. 2 events. Oh, by the way, this could be extended. I should mention that. This could be extended to more than 2 events. Okay? This could be extended to more than 2 events. So in general, this is what it will be. Everyone look up. Probability of intersection. So this is what the general thing will look like. So probability of intersection of some event AI, I from 1 to n. Understand? That is A1 intersection A2 intersection A3 intersection A4 intersection A5, something like that, will be, can somebody help me write the other side? Tell me what I should write first. Come on, try.
Is it like big pie?
Big pi, of course. Be confident. Trust yourself more than your cat. So this will be I from 1 to n of what? AI. That is not, oh wait. PAI, right?
Yeah.
Probability of AI. Not artificial intelligence, please. Okay? So this will be the general situation. Could be extended, of course. So 2 events are said to be dependent if the occurrence of one does affect the occurrence of the other. So in this case, probability that A and B occurs. Everybody look. Probability that A and B occurs is probability of A, because the first one is not a problem, right? Right?
Yeah. Yes.
Yes. Yes. The first one is not a problem, times the probability that B occurs given that A had occurred. Understand that?
Mm-hmm.
Probability that B occurs given that A has occurred, because that is the one affected, the second one is affected. Given that A has occurred. I will introduce you to a new symbol tomorrow. given that A had occurred. Okay? Because this is what will lead to conditional probability. We will divide this, then we'll be able to calculate the conditional probability of B given A. We'll do that tomorrow. Okay? And we extend it to Bayes' theorem on Thursday. You don't need to memorize this. You just work it out the way you've always been doing. Well, I'm just writing, the normal stuff that we show. So, look, everyone. Everyone listen. This is how you might deduce that something is dependent or independent event. If you are dealing with events, maybe like in a selection case now, and you are dealing with without replacement, would that be dependent or independent? Without replacement case, will it lead to dependent event or independent event? Say that again? Dependent, because if you do not replace, what you have picked, what you are going to pick next, depend on what you must have picked. Am I making sense? If you do not replace, what you will pick next, the chance of what you are picking next, is determined by what you picked at first. That's why we say probability of picking both now is probability of the first one times the probability of the second one, given that, which depends on what you have picked before. So when you do not have replacement, you are dealing with this situation. But when you have replacement, it doesn't matter. I have these pens. Probability of picking, let's say these two are indeed blue, even though we know they're not. One is purple. Let's say they are blue, right? Probability of picking a blue next, after I pick this one, if I put this back, does it affect anything? I still have 2/5. If I wish, I could pick this first. I put it back. Picking a blue is still 2/5. In fact, if I pick a blue first and I put it back, what is the chance of still picking a blue? 2/5. So if I'm dealing with replacement, I'm dealing with independent events. So that's another way to look at it. Okay? So let's take note of that before we write this example. Notes. In most cases, without replacement, okay, maybe I'll just write it straight line. In most cases, without replacement problems lead to dependent events, while with replacement problems involve, oh, I think it's the other way, right? Yeah, involves independent events. Okay, so this will come in handy for us. Now I want us to take the last 12 minutes to do the following examples together. Due to the time, I will not be able to do all the 5 that I highlighted. So how about we just try 1, 5 here, 7, then maybe the last one. So I'm picking exercise 11G, question 5, and question 7, then exercise 11H. Question 3, 7, and 13. So there are 5 of them, but I'm afraid we cannot do all the 5 because of our time. Okay, let's take a picture very quickly. So we only have 10 minutes. This is why we need to always try to work faster, okay? So that we do not, because I don't want this to take to tomorrow. Okay, everyone, please listen. Question 5 on the board. It says an archer hits the blue bullseye on average of 2 out of 5 shots. If 3 arrows are fired at the target, determine the probability that the blue eye is hit every time, first 2 times, not on the 3rd shot, on no occasion. So there are 3 events here, right? What is the first event? The first shot, right? The second shot is the second event. The 3rd shot is the 3rd event. Are these 3 events dependent or independent? They are independent, provided every other constant, every other factor is constant, right? Not like it started feeling cold suddenly, you know, or maybe after eating the first one, it got discouraged, or maybe something encouraged him. Let's leave all those constants out of the all those factors out of it. So, because they are independent, we just have to find the probability. So there are ways you could write directly, or you could use a tree diagram. Okay, if I write directly, probability of hitting that, the bullseye, I just say probability of E, for example, will be 2 over 5, yes? So which means the probability that it does not is 1 minus 2 over 5, which is 3 over 5. Understand? So the first situation, every time means probability of E, E, E. Am I right? And that will just be 2 over 5 times 2 over 5 times 2 over 5, because basically it's probability of E times probability of E times probability of E, because they are independent. Understand? So B, whatever that is. First 2 times and not the 3rd one. So it hit the first 2, but it does not hit the 3rd one. Can somebody tell me why I do not need to consider the permutation of this? Why not E prime E? Because there are possible ways. Can somebody tell me why I do not need that? Say that again? Even if they're independent, sometimes you will need to consider the possible orders. Say that again? You already give us the order. The first 2, they never said 2 of them will eat and 1 of them will not. If that was the case, then you need to consider, oh, what if the first one did not? What if the second one did not? Because this is the case of the 3rd one did not. All right? Then there will be 3 possible cases. Here, there's only 1 case because the order is already indicated. So you have 2 over 5 times 2 over 5 times 3 over 5. You can complete that. And on no occasion, that's just E prime, E prime, E prime, right? You have to be careful. On no occasion is not necessarily 1 minus all occasion. That would be 3 over 5. 3 over 5, right? Yes. That would have been 27 over 125, isn't it? This was 8 over 125. So do not use complementary events and say, oh, on no occasion is 1 minus on all occasions. Because there are other sub-occasions in between. And you can see that clearly if you had used your tree diagram. If you use tree diagram, this is the first shot. If the blue eyes does not hit the blue eyes. The fact that the first one hit the blue eyes, the bullseye, why did I say blue eye? The fact that the first shot hit the bullseye doesn't mean the second will or will not. So in the second shot, you have two possibilities, regardless of the situation. That's how you draw your tree diagram. So which means if the first one is, the second may, and the second may not. If the first one does not, the second may, and the second may not. Now this is shot 1, this is shot 2. There are 3 shots fired, right? Shot fired. So the fact that the second one does this does not mean the third will, and does not mean will not. So you have this scenario. So again, it, will not, it, will not, E prime, E prime. So you realize this is all occasions. This is non-occasion. You can see the other possibilities there. So you can't use complementary, because there are sub-possibilities there. But addition of all these possibilities gives you 1, because this is every possible scenario. If you draw your tree diagram and if the sum of these chances does not give you 1, then something is wrong. So let's see, especially in independent event. This is 2, right? Then this is 3. So 2 over 5, 3 over 5. You completed 2 over 5, 3 over 5. So for the first question, this is what you are looking for. This is question A. Right? For the second question, you E prime, right? E prime. This is what you are looking for. So if the order was not specified, another possibility is here. Another possibility is also here.
But would it be different?
Okay, the difference is, this says the first 2 times. So it's specified, while not on the third shot, right? So it could have been one of the shot did not eat. So one of the shot did not eat could be the first shot did not eat, the second shot did not eat, or the third shot did not eat. So there are 3 possibilities. But here it was specified that the third shot did not eat.
So the result would need to be times 3?
No. Exactly. Or you just add, these branches together, provided they are the same probabilities. Visually, it should be the same probability. Okay? So quickly, I have say 3 minutes. Now, that's the first one. So 2 ways you can do it. I'm happy to do 20 minutes, whatever, tomorrow. The second question is 7. So maybe we're going to have to do the second part tomorrow, which is fine. The dependent, so you can practice on independent today. So the second one says 2 baskets contain 5 red, green apples. Celia chooses an apple at random from each. Is this a dependent or independent situation? You choose apple from each basket. It's independent, because what you pick the first one does not affect what you, because you are not talking about one basket, right? So we draw the tree diagram, so we have to draw that way. Then from the tree diagram, we have to pick this. We are picking 2 apples, right? So we're going to go into, wait, is it? Yeah, 2 baskets. So the number of baskets does not determine the tree diagram. Rather, the number of apples being picked. Okay, so let's look at it. 2 baskets, each contains that. Celia chooses an apple at random from each. Okay, draw the tree diagram to illustrate possible outcomes. Oh, okay. So what should be the possibility? Will it be red and green? Okay, yeah, let's red and green. From box 1, I think you might want to use, it says tree diagram, but I think you might want to use the tabular approach in this case. Okay, anyways. From the first basket, we can have red to be what? Red to be, the chance of red will be what? Oh, no. Everything now is 7, right? So the first one, 5 out of 7. Here will be 2 out of 7. This is the for box 1, box 2, right? Red. No. This is everything. Okay, so you can have
everything in the first basket, yeah.
Yeah, this is everything, right? So if you pick the second case is, this is the first selection.
Yes.
The second selection